In this video, we're going to talk about the most secure cipher in the world, why nobody uses it, and what we do instead. Now, if you haven't seen our video on classical ciphers, go back and check that out first. Now, you remember from the last video, we looked at three classical ciphers: the Caesar cipher, the Vigenère cipher, and the Enigma machine. Each of these ciphers leaks information. For example, the Caesar cipher leaks information about the frequency of plaintext letters because that information is preserved in the ciphertext. Now, the Vigenère cipher still leaks information because the message is typically much longer than the key, and the key is applied to the message by repeating itself over and over again. So some of that structure is still preserved. Then, of course, there's the Enigma machine, which leaks information about what the plaintext isn't. So, is it even possible to build a cipher that leaks no information at all? We actually can do this. It's called the OneTime Pad. The OneTime Pad looks just like the Vigenère cipher, but with three crucial exceptions. The key must be exactly as long as the message, no repeats allowed. The key must also be chosen uniformly at random. That means all keys in the key space must be equally likely to be chosen. And finally, the key can never be reused. Now, if you can satisfy those three requirements, then encrypting a message with the OneTime Pad is just the same as the Vigenère. Each letter of the key corresponds to a position in the alphabet, and you transform the plaintext character by moving it forward that many spaces in the alphabet. Now, here's the magic of the OneTime Pad. If I gave you a ciphertext and I asked you to tell me what the message was, you've got a problem. Because the key has to be as large as the plaintext, that means that the key space is as big as the plaintext space. If I wanted to make a guess about what the plaintext was, I could make a guess about what the key was. I could apply that key to the ciphertext to get back a guess about what the plaintext was. So here's what this means. For any ciphertext, there exists some key that will decrypt it into any possible message. And what that means is that you get no information about what the plaintext was. We call this information theoretic security. What this means is that the OneTime Pad is unbreakable in the sense that all the computing power that ever was and ever will be would not help you to recover the message. It can't. Every key was equally likely to have been chosen, and there is some key that will transform your ciphertext into any message. So you just can't tell which one it was. Now you're saying, wow, this is great, unbreakable cryptography. That's nuts. Why don't we use that every day? Well, there's a few practical problems. They're not little problems either. They're big problems. The first one is that the key has to be as long as the message itself. So all you've really done is taken the problem of securely communicating a message and you've traded it for securely communicating a key. So if you wanted to use a OneTime Pad to encrypt this video, you would have to take hundreds of megabytes of data and somehow securely transmit it to Mountain View for every video you wanted to watch. And then you would have to have them store it until you were ready to receive the video. Then, if either party ever reused any portion of the key material, all of the perfect security properties are broken. So in practice, what we want is a single, short, fixed-length key that we can use to encrypt all kinds of data. This isn't information theoretic security, it's computational security. Remember, in this model, brute forcing the key is still possible, even though it might be hard. So what should it mean for a cipher in this model to be secure? Well, the OneTime Pad reveals no information about the plaintext given the ciphertext. So it'd be really cool if we could capture a similar idea in the computational security model. This leads us to an important security concept called semantic security. Here's how it works. Imagine Alice and Bob are communicating in two different universes. Now imagine in both universes, all the computers in the world are trying to recover some information about the plaintext. Now imagine Kerckhoff's principle applies in both universes. That means that in both universes, these computers receive information about which cipher was used and even how long the ciphertext was. But in universe A, that's all these computers get. Universe B, they get the same information except they also get the ciphertext. So obviously, if you don't have the ciphertext, you're not going to be able to do decryption. However, in universe B, since they have the ciphertext, they can try to brute force the key, and there's a non-zero chance that they'll just get lucky and find the right one. So universe B has a small advantage over universe A. So if we can formalize what we mean by the two universes being basically the same, and we can show that these two universes are basically the same, then what we're doing is we're saying that seeing the ciphertext doesn't give you any information. So this is what we mean by semantically secure. But how do we actually go about proving that a cipher is or isn't semantically secure? In order to do this, we're going to play a game. Not a fun game like Minecraft or baseball. It's an abstract game, like game theory. It has players, rules, and some kind of winning condition. This is a game about encryption. The game's going to involve some cipher. The game goes like this. I start by picking two messages from the plaintext space. Any two messages I want, and I send them to you. Then you flip a coin. If it's heads, you pick the first message, and if it's tails, you pick the second message. Now, whichever message you pick, you're going to encrypt it using the cipher and a particular key. We call this the challenge ciphertext. You're going to send the challenge ciphertext to me, and now I have to guess which of the two messages you picked. If I'm right, I win. We're going to call this the eavesdropping game because it models what it would be like for an attacker who's eavesdropping a communication channel. Now there's a few interesting implications of this game. The first is, if I guess randomly, I will win 50% of the time. Remember, you're picking the message with a 50-50 chance. If I also pick with a 50-50 chance, our guesses will be the same 50% of the time. Second, if I have any ability at all to distinguish the ciphertext, I can win this game with a greater than 50% chance. If I can't distinguish ciphertext, I can't do better than 50%. But even if I use a strategy that causes me to win less than 50% of the time, I can always just take my strategy and then guess the opposite of whatever my strategy says, and then I will win more than 50% of the time. So the advantage I have in winning this game is how far off of 50-50 I am. Remember, if I'm less than 50, I can always just guess the opposite to become more than 50. So is my advantage in the eavesdropping game ever zero? Well, no, because I get the challenge ciphertext, which means that in principle, I could try to brute force it, and there's some probability that I'll get lucky and find the right key. Depending on the ciphertext, it might be a small chance, but it's not zero. So how small is so small it basically doesn't matter? That's what we're interested in formalizing. This brings us to the notion of what's called a negligible function. We're parameterizing this function in the context of the security parameter of the cipher, the key length. And we say that we have a negligible advantage in winning this game if our advantage is less than or equal to a negligible function in the security parameter. In other words, our advantage is less than or equal to a number that's so small we don't care. We say a cipher is indistinguishable under eavesdropping if there is no probabilistic polynomial time Turing machine, essentially an efficient algorithm, that can win the eavesdropping game with an advantage that is greater than negligible. Okay, so how would you use this definition to prove that the Caesar, Vigenère, and Enigma ciphers are not indistinguishable under eavesdropping. What challenge ciphertext would you pick? What algorithm would you use to make a guess about the challenge ciphertext? And what advantage would this strategy give you? However, it turns out in practice that indistinguishability under eavesdropping is too strong a security notion. It's unreasonable in practice to assume that eavesdropping is the best an attacker can do. What if we look at some other models that grant the attacker additional powers? One such power is called the chosen-plaintext attack. The chosen-plaintext attack game runs exactly the same as the eavesdropping game. The only difference is we give the guesser an additional power, the ability to make encryption queries. What that means is that I, as the querier, can ask you to do some encryptions for me. I can send you any plaintext I want, and you will send me back the encryption of that plaintext under the same key that you will use to encrypt the challenge ciphertext. What that does is it allows me, as the querier, to potentially get some information about what the key might be. Now, if I cannot get an advantage distinguishing ciphertext, even though I have the power to ask you to encrypt plaintext for me, then we say the system is indistinguishable under chosen-plaintext attack, IND-CPA. Indistinguishability under chosen-plaintext attack was the original framing of the notion of semantic security by Goldwasser and McCallie, who won the Turing Award for their work. Now let's consider a game that gives the guesser even more powers. We call this the chosen ciphertext attack. It runs exactly the same as the chosen plaintext attack, except that as the querier, I also have the ability to ask you to decrypt messages for me. The only restriction is that this power runs out when I submit the challenge plaintext. If I cannot get a non-negligible advantage winning the chosen ciphertext attack game, even though I have the ability to request you to decrypt things for me, then we say that the system is indistinguishable under chosen ciphertext attack. But we're going to make a distinction here. We're going to call this the non-adaptive version because there's an adaptive version. The non-adaptive version, we call it IND-CCA 1. And finally, there's something called the adaptive chosen ciphertext attack. It proceeds exactly the same as the non-adaptive version, except that you can continue making decryption queries after you've received the challenge ciphertext. The only catch is that I cannot ask you to decrypt the challenge ciphertext for me. Otherwise, what's the point of the game? But that doesn't mean that I couldn't take the challenge ciphertext and modify it in some trivial way and give it to you and ask you to decrypt it. Now, if, despite all of this, I still can't get an advantage in winning this game, despite all of these powers, we say that the cipher is indistinguishable under adaptive chosen ciphertext attack, IND-CCA 2. Now that's the standard that we apply to cryptography that we use on the internet today. So for example, the security protocol that's encrypting this video stream right now is secure under adaptive chosen ciphertext attack. Now this may seem abstract, but there are real-world situations where it is possible for real-life attackers to make these kind of decryption queries in roundabout ways, which is why we need a security definition that's like this. Now I've described these attack models in very informal terms. If you'd like to read a more formal definition of these security levels, check out this textbook by Katz and Lindell. I'll leave a link in the description below. In the next video, we're going to look at some examples of modern ciphers and see how these security notions apply. Well, that's it for this video. If you enjoyed this, don't forget to click like and subscribe, and we'll see you next time.